Thank you so much, everyone, and welcome to our session, how to migrate your Spring Cloud microservices to fully managed services on AWS. So 10 years ago, I led the big transformation of a monolith to microservices using the Spring Cloud framework, hosted on self-managed servers, which proved to be a very challenging task to maintain. So in this session, Dennis and I will be discussing what we would have done differently if we had leveraged the power of the AWS cloud and its fully managed serverless services. So my name is Lefteris Karageorgiou. I'm Greek. I work for AWS. And prior to that, as a solutions architect, and prior to that, I was a software engineer for more than 15 years, working primarily with backend and Java. Dennis?
Yeah, I'm Dennis. I'm from Germany, north of Germany, actually. Great being here in Greece. I do 20 years of Java as well, working with enterprise customers at AWS. So we are colleagues, but just covering different regions. And I will be happy to present this second part to you.
Awesome. So who in here is a Java developer? Awesome. And who in here loves Java? Less hands, right? Who in here hates Java? Awesome, we have haters as well. Amazing. Now, I'll start with a famous quote by Amazon CTO, Werner Vogels. Everything fails all the time. And that is the case for almost any software that we will write in our careers, right? Usually when we start, we build a state-of-the-art code base, which is like a small code base, very easy to read, very easy to maintain, to understand, to test, to deploy, and we are very happy as developers. But as soon as we start adding new features, this code base becomes huge. It is very hard to understand, to read, to maintain. The deployment might take like several minutes, up to 30 minutes, and it might fail also in production due to memory or CPU issues. So what we should really do is somehow break down this monolith into smaller services. Around 2010, a new architectural approach came into picture, which was called microservices. Now, microservices promised to solve many issues that a monolith had, but unfortunately, it introduced many, many other problems into our platform. Now, microservices must follow several design principles. For example, each microservice has to be autonomous. It has to implement one specific functionality or business capability. Also, microservices should be independent from each other. They can be deployed, they can be scaled, they can be tested independently. And last but not least, microservices are designed to gracefully handle failures of other services. So, if only one service fails, then the entire system should remain operational. Let's now go through an architectural diagram of a microservices architecture and see what components we have to have in order to build a proper microservices architecture. In the middle to the right, you see the microservices that contains the business logic. Now, some considerations and concerns we might have for those microservices that contain the business logic are, one, scalability. How much can the system scale? Can our microservices scale? Can they handle the traffic we have? Or do we need to add new nodes and new instances of this microservice? High availability. Is my system highly available all the time? What can I do to have it highly available? Okay, you'll tell me I need at least 3 nodes of a microservice, and that will make it highly available, right? Then we need to allocate CPU and memory for a microservice beforehand, before we ship it into production. We have to know the memory and the CPU, and that is a very hard thing to do. Also, we need to support various runtimes. You might have like Java 17 or Java 8, or you might have Quarkus or GraalVM or whatever runtime. What other components do we see in this architecture here? We have API Gateway, which acts as the front door of our system and handles all the requests and routes them to our backend services. For an API Gateway, we have so many considerations and concerns. For example, we need to define the protocol. Is it going to be HTTP API or REST API or WebSockets? We need to have versioning. I mean, that is a pain already, right? How do we version our APIs, like V1 or a question mark V in the request parameters or in the headers? How do we version our APIs? How can we have caching at the API gateway layer so we don't send all the requests back to the backend server? We can have throttling, so we can secure our APIs for too many requests that come into our system. Then we have authorization, which is a bit tightly coupled with the authorization server we see on the right. So this is how we authenticate, we authorize our APIs. How do we create JWT tokens, for example, to be passed on to the backend server? SSL certificates is also another pain. We need to attach an SSL certificate to our API gateway. We need to renew it. We need to do many things. And then we need to have some kind of web application firewall in order to secure our APIs from attacks like SQL injection or whatever attack, or say, I want this IPs to be whitelisted, or I want these IPs to be whitelisted. So many considerations. As soon as we get the request and we go to the load balancer side, the load balancer is responsible to send the request to the right set of microservices. And because we might have like many nodes of the same microservices, the load balancer needs to be aware of which microservice is healthy. So we have to have a load balancing algorithms like a round robin, so each node of microservice will get one request, or we can have a list outstanding requests load balancing algorithm. And for those to happen, a load balancer needs to do health checks. Another component that we have to have in a microservice architecture is service discovery. Imagine you have like hundreds of microservices and each other do not know the IPs and the ports that they expose. So what they actually do, the microservices, they try to register themselves in the service discovery service. And then all the other microservices will find from this service discovery the IPs and the ports of the microservices. We also have a configuration server. So imagine like a central repository, like a Git or a file system or whatever, where you have all your keys to manage them and also to rotate them. Last but not least, in all this microservices architecture, we need to trace the requests from the start to the end, to the backend server, right? And for that, we need to have distributed tracing. And distributed tracing is not only about traces, it's also about observability and monitoring, to have metrics and have loggings all the way the request to the backend server. Things get more complicated when we introduce the circuit breaker pattern into our system. And who here knows what circuit breaker pattern is? Awesome. Now, the circuit breaker pattern says that if service C fails, for whatever reason, I have a bug in my system, I mean, CPU or memory has peaked, I don't want the request to fail, but I want it to be sent to a fallback service. which is service C failover, for example. And this service C failover might contain like a subset code for our microservices or like a different code. Now, 10 years back, the very famous Spring framework released the Spring Cloud Framework, which implemented all of those components that we see here in the microservice architecture. For example, for API Gateway, there is the Spring Cloud Gateway, we have the Spring Cloud Load Balancer, we have Spring Authorization Server, we have Spring Cloud Netflix, and Netflix was one of the first major companies that implemented microservices in 2010, and that is why microservices became so popular, because of Netflix. For the microservices that contain the business logic, we can have Spring Boot, as I said, we can have Quarkus, we can have GraalVM, or whatever, right? Now, take all those components and sum up how many JVMs we need to have up and running for just 3 microservices that contain business logic. And that is 33 JVMs we need to have up and running. We need to allocate memory. We need to have servers started on servers for only 3 microservices that contain the business logic. And the question is here, can you actually administer, maintain, operate all those servers for just 3 microservices? How do we actually shift this operational stuff to only focus on our business logic? Now, a study by Deloitte in 2019 showed that only 20% of the time developers take for code to code, only 20% of the time. Now, 80% of this time, you focus on maintaining the servers, start up the servers, and all those crappy stuff. So how do we shift this focus to the business logic? And the answer is with serverless technologies on AWS. What do we get with serverless on AWS? First of all, you do not need to manage any infrastructure. AWS will do that for you. You do not need to start up any server or maintain the server or patch the servers or update the operating system, nothing. You just focus on writing the code. You do not have to worry about scaling. Because with serverless on AWS, everything auto-scales without having to do, you as a developer having to do anything. Also, you pay only for what you use. If you do not use the serverless services, you do not pay anything. This is a pay-as-you-go consumption model. And you have a highly available infrastructure. You do not need to do anything, and with built-in security as well. What we will be doing in the next 25 minutes is, from this architectural diagram that we saw before, is replace each component with an equivalent AWS serverless service. We will start with Spring Cloud Gateway, which is the API gateway with Spring Cloud Security and the Spring Authorization Server, and see what technology we will use in AWS. So the equivalent API gateway service for AWS is Amazon API Gateway. With Amazon API Gateway, you do not need to worry about administering any server and maintaining servers. What you actually do with Amazon API Gateway is, first, you define the protocol. Is it going to be REST, HTTP, WebSockets? And then you define the integration, where I want this request to route. I want it to route to a Lambda function, I want it to route to another AWS service, or to any publicly accessible endpoint that you might have on-prem. You deploy the API, you get a URL, and boom, that is all. You do not do anything. Let's see also some features that an API gateway has, because we talked about some considerations and concerns in the previous slide. API gateway supports a caching feature, which has a massive amount of capacity. It can go up to 237 gigabytes. So if you want to cache your requests based on the URL, on the request parameters, on the headers, on path parameters, whatever, you can do it on the API gateway layer. And under the hood, API gateway uses Amazon EC2 instances to actually do that. Amazon API Gateway also seamlessly integrates with AWS Web Application Firewall, or WAF. So, if you want to whitelist or blacklist any IPs, you can easily do it through a few clicks. If you want to get protected against common web exploits, such as SQL injection, cross-site scripting, and others, you also can do it with AWS Web Application Firewall. API Gateway also seamlessly integrates with AWS Certificate Manager, and that is a really pain for most of us. I remember back in the days, you would have to create a Jira ticket and say to your ITs, please do not forget by the end of this month to renew my SSLs because it will expire and I will be out of business. But with serverless on AWS and with API Gateway, you can provision your SSL and TLS certificates for free, and also those will be renewed automatically. So you just do it once and you never touch that again. You also have the option to bring your own certificate as well. Another feature that API Gateway has is stages. Now, with stages, you can have versioning. You can have, for example, a prod v1 version that is tightly coupled with a deployment, for example. And if you want to have a new deployment that has version 2, for example, you can create another stage, production v2, and point that to the new deployment. Now, what about throttling? I mean, how many servers do you have to deploy if you have Apache server or an Nginx or whatever to get a fair amount of requests per second? With API Gateway, by default, you can get 10,000 requests per second. And out of those 10,000 requests per second, 5,000 can be processed concurrently. And these are numbers that can be increased if you open a ticket with the AWS support team. Moving on, let's see what we would use for the authorization server. Amazon Cognito is a fully managed application identity service. Imagine it has a directory, database, where you can create your users based on a username, password, email, and any other attribute you'd like to have. And you could get a nice UI if you want to use this hosted UI, where you can do your registration, your logins, and then this will route to your backend, for example. With Amazon API Gateway, you can also create JWT tokens, and that is done automatically for you, and those are being used by Amazon API Gateway without having to write any code at all. Also, Amazon Cognito offers federation with other identity service providers, such as Google Login, Facebook, Amazon.com, and any other OAuth 2 compliant service. So what we have done already is replaced our API gateway with Amazon API gateway. We have replaced the security with a web application firewall and our authorization server with Amazon Cognito, and we no longer need to maintain any servers. So Dennis will continue with the rest of the presentation and show you how to replace the remaining components.
Thank you, Lefteris. Okay, the good thing is it's an iterative approach, so ideally we could also stop now, but the issue would still exist. We have now a mixture of some serverless services and some services that are already serverless. So we continue. And the next step is actually where to run our Spring Boot applications. And there are a multitude of ways, right? And we just show you 2 ways today, just as a basic decision. So the one thing is run the Spring Boot application in a container. And the other thing is run the Spring Boot application as a serverless function. And to do that on AWS, you can leverage ECS, which is the Elastic Container Service, along with Fargate, that's the underlying compute layer. There are other options, like you could also use AppRunner, it's a different kind of abstraction. You could also use Kubernetes, but both of us, we are not that a fan of Kubernetes. So for now, we just show you the option with ECS. And the other option is running on AWS Lambda. The 2 differences between the approaches is basically a container is more ideal for long-running services if you are continuously receiving requests, for example, and ideal for a traditional web application and other workloads, of course, as well, like batch processing or something like that. On the other hand, the serverless functions in Lambda, they are more short-lived, so you have a shorter request duration and ideal for event-driven applications. And if we emphasize on the differences again, on the left-hand side, the container services compute-oriented, so it's still focused on the underlying compute, although we abstract it with a serverless layer, whereas Lambda is event-oriented. So there we really have an abstraction. The infrastructure is no longer visible, while with the container services, we help you managing it more efficiently and more easily, right? And the main thing also for you in the end is a price. So for the container services, you still pay infrastructure consumption-based, while on the right side, it's request-based, so you pay per duration. Those are the main differences. And actually, many customers just run both, so it's a mixture of both. What we will do today with our Spring Boot applications, we will run them on Lambda, because for us it's very, very compelling. And the question is, how does Lambda actually work? For those of you who've never seen it, just a quick overview. I just need to click once more. Here you see a Lambda function, and Lambda function is your application code, and it's a framework or some libraries around it. So that's what you can run on Lambda, and the service itself, it handles capacity, scaling, patching, administration of the infrastructure. That's all handled by the service. There are no servers clusters involved in your view, because we abstracted away for you. And it also scales to 0, which means if there's nothing going on, the service just scales down and you are not paying. So that's very compelling. How is Lambda triggered? I already said it's event-driven. So we react to events with Lambda, maybe a change in date state, maybe request to an endpoint like the API gateway that we've just seen. Or there may be other things like a file got uploaded somewhere and I want to respond to it. The difference compared to containers in request handling is this. A container application, you just initialize it once, it boots up, the container is there, and then we can continuously serving requests with a running container. And if we need more capacity, we will scale it up and run the container in different instances. But in general, we can leverage the features like multi-threading in Java. If we have the Tomcat, which is the underlying thing in Spring Boot, the same container will be able to handle multiple requests. With Lambda, it's different. So once the request arrives, we will create a new execution environment. This gets initialized and is able to serve a request. So, and when the next request comes in, and the execution environment is available, it may be also available to serve this request. But if a third request comes in, we need to create another execution environment. So, and we have that here. It needs to be initialized again. So, and there you also see with Java applications that may lead to a problem because initialization takes a bit of time, right? So, but we have also certain, I'd not say workarounds, certain features against that. We can snapshot the environment, but it would probably be a bit too much to show you all the techniques in 20 minutes. So you can just, you need to pay attention to that initialization time matters when we talk about Lambda. So, and this is another one. It can be executed in the first environment again. And if there are no requests coming, the environments will be shut down and no longer existent until the next request arrives. So that's very compelling because it scales to 0. And the only question for us is, we have our existing Spring Boot applications, and they may exist, as we heard, like 10 years ago. We built this fancy microservices apps, but yeah, we didn't really pay attention to building them in a event-driven fashion. So what can we do if we are not that event-driven in our Spring Boot application yet? We don't want to rewrite the whole thing. We just want to take it as is, but Lambda still sounds great for us. So we use a pattern and build an adapter between it. So, and one way of doing it is we have a library that is called AWS Serverless Java Container, which is on GitHub, so it's open source. And that's basically something that you just plug into your existing application. So if you have the Maven POM, for example, you just add the library, and it interacts as a layer in between your application. It receives the events from the API gateway and just translates them to the classic servlet requests that Spring understands. And we actually created that together with the Spring team. So we are working closely with the folks at no longer VMware, it's now Broadcom. But that's how it also integrates with Spring Cloud Functions, Boot, and Framework. So that's pretty easy because you just add the library and then you are done for now. You can still refactor it or optimize it later on to be more cloud native and more event driven, but for now it just works like that. And this is what we apply here. So we replace all of our Lambda functions, all of our Spring Boot applications with Lambda functions. So the load balancer in the middle, you see, the question is, do we still need it? And the answer is no, we can replace it actually by just taking it out, because Lambda natively integrates with API Gateway. There is no separate load balancing needed in between. That is what comes out of the service. So scaling is also done by the service itself. There doesn't need to be another load balancer. You can do it if you want to, but it just saves cost to remove this component out of the architecture. Then we have service discovery on the right, Spring Cloud Netflix. So how do we know where the services are deployed? How can they find each other? We have a service for that, which is called AWS Cloud Map, that allows you to do this service discovery. So it's, for example, if you have different versions deployed, there will be a central registry where you can look up which service is deployed where. So it sounds ideal, and if you Google for it, you may just find it and say, hey, this is something I want to integrate here. But do we need it? And the answer is no, we can just remove it, because Lambda itself has a versioning feature, and in API Gateway, you can also directly point the endpoints to individual function versions. So there is no value add in using Cloud Map in this case. So I see many customers thinking that could be a good idea, but you no longer need it. You can just simplify the architecture and remove it here. Let's look at the circuit breaker down here. So the circuit breaker, as Lefteris introduced, it's for having a fallback, for example. If you have a foreign service that you are calling, for example, you have a payment provider, this payment provider is not available, what are you doing then? Or you have a different kind of API and you rely on it. You don't want to have a timeout like the customer waiting for it. So you use the circuit breaker pattern to switch over. And what we can leverage on AWS is AWS step functions. So this is a service that allows you to orchestrate different microservices. It comes with a UI, so you can use a designer to build it. In the end, it translates to JSON. So if you want to, you can also use the JSON directly. And it's not only for a circuit breaker pattern, you can also draw a nice little orchestration with it for a chain of service calls, but it works nicely for orchestrating the circuit breaker as well. So we built a little flow like that, where we check if the flow is closed. And we make the decision, as you see in the diagram, the flow is routed like that. So that's for us very convenient. And we can just replace the circuit breaker thing with this AWS step function. So it also integrates with API Gateway and Lambda directly. No need to write integration code or something like that. It's very convenient for us to do it. So just a few things left in here. I know it's a lot of services. And the best thing in the end, you will notice that's not the only choice. We could build different architecture diagrams with different components. That's just one way of doing it, kind of a best practice that we like how to do it. But you are welcome to discuss with us individually about alternatives as well. What we are now replacing is the config server. So there we have, like in a key value style, our configuration values and secrets in a central location. Like as designed per 12-factor app, for example, you want to externalize the configuration and not maintain it inside your code base. And what we can leverage on AWS is Secret Manager. So Secret Manager is a service that helps you to manage and administer the different secrets. And the best thing is also it helps you with credential rotation, because a lot of passwords never get changed because it's too painful to do it. And Secrets Manager helps with that and really simplifies it. And what you see here, it's, for example, handy if you talk to a database. So secrets get encrypted with Secrets Manager. And within my Lambda function, I can just fetch the secret. There's a caching functionality as well, and then I can use this password to access the database. Good, secrets are moved to Secrets Manager. So now it's just the last thing, but very important thing left, because when we saw customers moving to a microservices application, they were used to looking into a single log file out of their monolith to see what's going on and just dealing with a singular component. So observability has become increasingly important. And if we talk about observability, and for those of you who have not been to Nicolas' talk yesterday, or where he introduced the different pillars, so you basically want to deal with logs, metrics, and traces. And ideally, you also have some health checks and alarms where you, for example, you build an on-call flow where when something goes down, you want to do the alarming. So those are the basic parts that you need. And traditionally, you build it on every layer, right? You have something for your storage, for your hardware. You have something for the virtualization layer, if that is working, something on the operating system layer. in a container, in a VM, and up until some business metrics, for example, that your stakeholders are interested, like how many orders did you process. And with the architecture that we've just been built, it gets simpler because serverless has you covered. We are abstracting so much of the infrastructure that the only thing that you need to pay attention to is the application and data layer and the business layer on top of it. The rest of it, we'll take care of it, and you can directly get those metrics information and those logs and traces out of the services that we provide. Here's just as an overview the two directions that you can decide if you want to implement it on AWS. So there's one direction like AWS native services. Those are CloudWatch and X-Ray. Exist for a long time, very mature and very easy to set up. But customers told us they also like the capability to leverage open source observability on AWS. And that's why on the right-hand side, you see the different other options that also integrate well. Like Prometheus, Grafana, OpenSearch you see there. But you can also use partner solutions or Jaeger and Zipkin, like other open source tools, to implement that. For our architecture, we use X-Ray because that's well integrated with Lambda. You see nice little tracing graphs there. You can see where the time is lost. If you have a performance problem, you see which component or which Lambda function took the time out of an individual request. So that's our result. Basically, we walked you through the different microservices components inside the architecture, and we've shown you the different replacements that you can use. As said, that's not the only solution, and what you can certainly also do is, if you like a different provider, you'll find a mapping and you can identify similar services there as well, right? This is not only possible on AWS. What you should take away, though, is that managed services and especially the serverless options allow you to focus more on the business logic, right? So you can move away from handling the routine tasks like updating an operating system, maintaining certain things, increasing a table space or storage or something like that, because that's something that gets so much easier, and you get more time to focus really on the things that matter for your stakeholders, for the business where you can really make a difference. You may still choose, so it's not mandatory to use all those services, if there's a certain component in it where you say, okay, this is something we customized back then because there was a functionality not available and this really matters to us. We customize it and we want to keep it in a self-managed fashion. That's still possible, right? So if there are good reasons, you can still do that. It's like up to you how you build that architecture. You can also leverage alternative solutions. So for example, API Gateway is a service that we provide, but similar to how you have on the Amazon marketplace, you can buy stuff that's not coming and delivered by Amazon. You can use on the AWS marketplace components that are from third-party ISVs, like certain companies who just say, yeah, that's something that works great on AWS. And for an API gateway, for example, Kong is a famous API gateway that you may want to leverage there. Yeah, and last advice, if you ever do that approach and this kind of transition, take one step after another. So avoid the big bang thinking that you build an alternative architecture next to your existing one, but rather transition in smaller steps, right? And we are happy to help you with that. We have teams in different countries. We have a local team here in Greece, all around Europe, so don't hesitate to also reach out to us. We are happy to provide guidance for that as well. Some more resources are published on a website called Serverless Land. We have a dedicated Java section in there. So that's all around serverless, where you also find repositories with sample code. In terms of time, we had no live demo today. You find a workshop there also with a walkthrough. So that's very helpful for that. And with that, we are at the end of the presentation. I'd like to thank you. There is a survey on the mobile Devoxx webpage. I put in a QR code here because it was a bit hidden for me. When you initially open it, you get the big fat client webpage. But this is a mobile webpage, so we would really appreciate if you liked it and you'd like to see more content around Java in the cloud. If you just provide some feedback, that's super helpful for us. Now I wish you a good rest of the conference and hope to see you soon. Thank you.
Thank you, guys.
Thank you.
Thank you, Lefteris. Thank you, Dennis. And as always, we have a few presents for you. Here, the olive trees.
Thank you so much.
I hope you don't need to declare them if you're moving around.
No, but I think I need to plant it inside because in the north of Germany it's super freezy right now. That's the beauty of Greece.
Oh my goodness. Yeah, definitely.
Thanks a lot.
Thank you
Thank
so
you,
much.
guys.